Yeah, you can minimize it.
Maybe I should start.
Check the. It will be. Yeah, it's now available. Yes. So now you can minimize it. Yeah.
Okay. I will stand up actually.
Don't.
It's like
Just
camera thing
just
is like
sit.
capture me. So 先说一下，大家要先下载这个东西，这里面有我这今天要用的东西都里面都在。所以 Yeah, I got this like just now. So please.
What's the difference between the one that you presented on the OSF? We showed the OSF earlier to the students.
Yeah, OSF. But the thing is, today's presentation, I have rescoped the range of what we're talking about. So
Okay.
I will talk a little bit about actually effective connectivity stuff first,
Okay.
and then I will move on to some practice. Yeah, and I have the real code for demo
Okay.
as well. So it's better download this and you're gonna start on there. So okay, so let's start. So stuff I'm talking about is mediation analysis, and I'm pretty sure there is person who confused it as meditation analysis. Raise your hand right now, like you thought this is meditation or not?
That should be practice, not analysis, right?
Yeah.
Meditation practice.
Yeah, I saw it actually like when the first time I saw this like a function tab like in the mediation random effect mediation analysis, and I saw like why there's like a meditation stuff like here, like I don't get it, and I realized it's actually mediation. So it was like
In NeuroL, we know.
yeah, exactly.
That's cool.
So I guess today we have talked about GLM, parametric modulation, and the PPI is actually part of one of methodology for functional connectivity. And right now, actually I'm supposed to talk about mediation analysis only, but it's not really broad enough for 1.5 hour. So I included something else, and I'll talk about effective connectivity, about like concept, and I got some literatures and references. And I got some demos, and finally, I will use the NeuroL for the URF GUI for the random effect mediation analysis for our real data. Yeah. So I keep talking about this connectivity stuff, functional connectivity, effective connectivity. So PPI just Xiaoshan introduced. That's one of quite like it's like a seed-based correlation. One of the example of seed-based correlation, and if we got like this neuroimaging or neuroscience data, and connectivity is one of very good interest. Actually, one of interest, like how do we make inference between like regions, between brain regions, or between like channels based on electromagnetic or hemodynamic stuff. So functional connectivity tell us about this. So this is one famous paper that many people referring when they talk about this connectivity, and it was 2007 and PNAS paper. So we got at least 3 different connectivity: anatomical connectivity, functional connectivity, and effective connectivity. And this connectivity term connectivity can be measured by many different ways. And
what's the third kind of connectivity? What you just mentioned?
anatomical one.
Structure.
So for example, like
What is the effective connectivity?
effective or
Effective, the third one, yes.
third one, effective connectivity. Here this one used a little bit uncommon one. It's called they used like non-symmetric transfer entropy. I guess it's not common, but this is one of the example of this different kind of connectivity. So yeah, I'll talk about later. But so functional connectivity is tell us the association between like these regional between regional time series. So we have different like brain regions, and this relation between these regions can be inferred by correlation. And this, how do we estimate this correlation? Have like many different ways. Seed-based correlation, like Xiaoshan just gave, or coherence analysis is actually one of for the functional connectivity, or ICA, independent component analysis, PCA, or what, something else like VVV, yeah, whatever. So there's all kind of functional connectivity, but there's effective connectivity that actually I'm going to talk about. So what's the difference between functional connectivity and effective connectivity is yeah. What do you think? Functional connectivity, effective connectivity. So if functional connectivity doesn't tell us about this mechanistic insights, or how this between regions or between our region of interest can influence each other, and how they like sequentially like associated, like how do they influence each other, and how the like information from the input to our behavioral response, there's something going on in our brain like across like 4 or 5 brain regions, and we know like there's 4 or 5 brain regions associated somehow, but we don't really know like how this like goes through, like 1 to 2, 2 to 3, 4 to 5 or something like that. We don't know about that, and effective connectivity is the methodology to influence this part, this mechanistic insight. So that's the one thing, and yeah, this paper. So effective connectivity, as I just said, functional connectivity have different many kind. Effective connectivity have many different kind as well. So structural equation modeling, granular, for the fMRI at least, for the fMRI, this part. At least this 5 is pretty famous one. The structural equation modeling and granular causality and VAR, which is granular causality influence on VAR. I don't know. I didn't use it, so I don't know. But and dynamic causal modeling is pretty famous. And as you can see, the trend in here, actually DCM get more and more spotlight for addressing this effective connectivity problem. So, and then mediation analysis. And mediation analysis is pretty simple, and it's quite simple. And if you want to apply like a really complex model, then you need to consider like use SEM or DCM actually. So there's something you should mind. So I found out that actually DCM is pretty popular, and you get more and more citation and more spotlight. And mediation is still valid, and many people use it, but it's only for like a really simple model. So I will talk about DCM first, and I'll talk about mediation later for like just only the tip DCM. So part of the reason DCM get many users is one of big reason, I guess, is because it's actually default implementation in SPM. I guess we already got SPM, right? SPM is like one of the most popular neuroimaging toolbox in MATLAB, and DCM is basically like if you finish like pre-processing and GLM stuff in the SPM, then actually you can directly actually implement this DCM as well, because the author of this DCM and SPM is Carl Friston in UCL, and he just implemented it, and it's very like easy to use basically. But behind what's going on about this DCM, this modeling is really complex. So, but at least it's easy to use, and also it evolved over the time. Like there's so many different like DCM, like keep develop over the time, like behavioral DCM, nonlinear two-state, stochastic spectral, whatever, and so DCM seems like one of the popular method to address this causal model or inference about this kind of how information flows in the brain or neuroimaging data about this part. So DCM is quite something. It's quite complex model, and I will talk a little bit, so it's fine you don't understand, you don't get it right now. I know this course is crash course, and we already been through a lot of stuff today, and I only get little part about it. So DCM we have a neural states model which is modeled by this equation, and this neural state model for the fMRI, we use this balloon model to make it into the bold signal, and this bold signal is the model that we use later. We can see in the fMRI bold signal, and the part is what we control is the neural state model by how to say. So this is one of the example of neural state model. So this X is brain region 1, ROI1, X2, brain region 2, and we note that X1 effect on the X2, X2 can effect on X1, and UI is the direct input, which is the stimuli or task, and we say U2 is the modulatory effect that goes on between ROI to the ROI2. And then this neural state model stating this task and the relationship between ROI is later converted into the hemodynamic state model through the balloon model. And then we can compare this model to the real observation of our fMRI signal. So that's the idea of DCM, and that's how it goes. Stimulate function U to this XT neural state and hemodynamic state, and then estimate board response. And then we compare our modeled board signal and simulated our model, and then this board response. We can compare these two. So between model and the real observation, the inference between these two. So that's what's going on. Bayesian model inversion. And that's the Bayesian model inversion is what we use for making inference between this modeled board signal and then this observation measured board signal. How do we infer this part? Like how close this model and the real our observation can be inferred by Bayesian model inversion, and that's like using variational expectation maximization under Laplace approximation. I have no idea what it is, but and then later we have like different models to compare to see like which model is actually representing the real data best. So we need to like compare this between models. So when it goes on, we use Bayesian model selection. So that's DCM, idea of DCM. Okay, this is like the part, next part. So Bayesian model inversion, Bayesian model selection part. So that's the example of what we got in the end. So for example, we have like 3 different models stating three different neural states. You have 3 different nodes or V1, V5, SPC with 3 different regions. And we have direct input as a phodic, and we have this modulatory effect as attention. So we in this first model forward, we state V1 to V5, and then attention has modulatory effect between this V1 to V5. In the second model backward, have stating that SPC to V5 have modulatory effect of attention. And the third one, forward and backward, we include these two modulatory effect, this one and this one. Okay, so the results say, which is using Bayesian model selection, stating we compare like model evidence using Bayesian method and saying, yeah, say we have 11 subjects, and first subject have a model evidence. For the forward backward, the third model has the most representing with their real activation, fMRI activation, and second one as forward and backward, third, fourth, and subject 5, 6, 7 have this forward model is most fitting with the real their fMRI brain activation, and then go on. So the results saying, so for the backward model, which is stating modulatory effect of attention is in the V1 to V5, and then SPC to V5 between these brain regions, is best model to representing their brain activation for their own task. That's the DCM. Yeah. This is another reference to say like 2 different group. One group do the project.
In the previous one, do they control for like maybe Because as you can see from the first and second, the third one just combine the two, right?
Yeah.
Like in most of the statistics model will consider adjusted regress, adjusted R square. But in this case, do they usually take that into account?
Account for.
So, for instance, the model 1, the model 3 is a combination of model 1 and model 2.
Yeah,
right?
that is.
If you talk in terms of R square, usually we'll take into account that you have more variables in model 3 compared to model 1 and model 2.
Yeah.
So we're going to compare the effectiveness of the model. We usually use the adjusted R square.
Yeah.
But here it seems not take into account.
So
So the question is that usually in this type of causal modeling, when they compare which model is the best, do they usually take that into account?
Yeah, so that usually they suggest two. One is the log evidence, comparing the log evidence. Second is the classical model fitness, which is R squared. So.
But in this one, the log evidence seems not take into account that the third one includes more variables.
Yeah, but usually it does. There is like percentage to say that this goodness of fit of this each model usually is pretty high, and it's like corresponding with this log evidence. But yeah, I guess they didn't report it.
It's okay, I'm just curious.
So it's another example of this DCM. So like for the projector group, they have like this bottom-up process between visual area cortex, RSA, V4, SPL. Associator group, they have different model, and they use the DCM to suggest this bottom-up processing, top-down processing modeled by these three brain regions and association can be actually differentiated by their Bayesian model inversion stuff. Okay, so projectors have much more evidence to say that this bottom-up model is actually what's going on in their brain regions, which have more fit for their fMRI, and then for the associators, they have more evidence to state that provide the support that their top-down model is more represented on their real fMRI. So, and then they well represented these two model with this Bayesian, and yeah, they got published in the JNeuro in 2011, and only two figures only did the DCM, and they got published. So I think that's pretty impressive. Okay, so I was going to like show a little bit more about this DCM actually, like. So if you check out the file folder that I shared previously, there is a code called demo DCM, motor premotor practice. But prior to this, I used this VBA toolbox. I already included in the folder. So this is the one of the toolbox that actually implementing this variational analysis method. So variational doesn't mean it's not the adjective. Okay, variational is the terms for stating this analysis method. So this VBA toolbox implemented a lot of code and a lot of models we can test this variational Bayesian analysis, and one of them was actually DCM. So I downloaded it, and I'm using it right now, and it's really easy. You just download it and you just set pass. That's all you need to do. Okay. Where is it? Where is set pass? So only thing you need to know is like just include as subfolders and save. That's how that's done. Now you can use it. Okay. Okay, for the demo, what's going on? So what we keep talk about some of this variational expectation maximization stuff is because when it comes to this DCM model, the parameters, the parameter we need to estimate for the model is at least like a 10, 20, 30, or keep goes on, you know. There's a lot of parameters we needed to estimate, and classical method maybe definitely not really, you know, maybe computationally like too not efficient enough, or other methods maybe, and so that's why this variational method comes out, and is used for this DCM stuff. So the neural state is defined, is structured by this ABCD, which is stating A state this ROI between ROI fixed effect, B state modulatory effect, C state direct input, and D state some other effect, but you know, I'm not going to talk about it. Okay? So this here, I will just initiating this stuff. You know, I'm not really going through like everything. So, but I'm just, you know, let's just talk about it later. Let me initiate stuff. So what I'm going to do here is, so we have this task. Okay, I'll use something else, you know, later. So we will simulate a data for the DCM, and then we will structure our model, and we will apply this model for predict the simulated data and see whether they can predict or not. Our model can predict the simulated data or not. So that's the just simple experiment. Okay. So we got some stuff. Let's show it. Just imagine this as task design. This is like our neural state. Like for the condition 1, we have like this 4 epoch, and for the condition 2, we have epoch, but like a little less. Okay, and this is simulated data, how it look like. Okay, this is simulated one. So I will now structure the model for the DCM and see whether our model actually can show this, can predict this data or not. So here we go. So I talked about this ABCD stating direct input or fixed effect or modulatory effect. So we have these two brain regions, just imaginary brain regions, and I'm right now put their relationship between these two. So when I simulated it, actually, like I have this simulated brain models first, yeah. So right now, but without like thinking about it, yeah. So you have this ABCD. And for the Bayesian model, we need to set up these priors. So we already have this 21. We have 21 parameters to estimate, and they have like consists of like 10 hidden states. And okay. Very unfortunately, I cannot see. The screen is too small. The screen is too small. Crap. Yeah, we got this. Okay. You know what? I'll do it again. So as you can see, so this variational Bayesian inversion, we use this VBA, and we have estimated these 21 parameters, which is fit best for our model and to our observed simulated data. And in the end, we got like 86% 5 for their fitness, and for the log evidence, we got like a really strong evidence to suggest that they are actually our model predicted the simulated data, which is not surprising actually. And I have like another model that I will show, which is different from the model we used for the simulation, and see whether this can predict or not. Let's see it. This takes a little bit longer. As you can see, like it keeps changing, you know. It's for the optimization of parameters. You can see like this parameter keep changing and converge into the most fit for the simulated data. But sometimes it doesn't work, you know, because this model actually, the model that I just used is actually like well fit. But when it just comes out like, you know, some random models, then it probably, even at their best, it doesn't fit yet. So that's what happens. So 86% with 351 log evidence, so it's pretty fit well, and even compared to the previous one. Oops. Like this guy. You can see I used two different models, and you can see it's two different fitness, and the second model actually fit a little bit better than the first one. As you can see, or maybe not. Yeah, maybe not actually. First one was better. 86% 0.5, 86%. So whatever. It's pretty similar. Yeah. So that's DCM. And I just say this. I talk about this because DCM is one popular method, and actually really good to. I think it's worth to share for everyone. So, but I'm fine. I think it's fine if you don't really get it right now, I guess. So that was DCM, and I'll talk about mediation. So the reason is like mediation is quite simple, and maybe it's too bored or something. So that's why I introduced DCM. So let's show like some cool stuff, you know, some math and the kind of things, you know. So. Okay, for the mediation, I'm going to use a code, demo mediation analysis practice, August 620. This one, this guy. I use this code, so take a look if you can. So the mediation analysis, what do you think? Meditation analysis, what do you think? So if we have like two variable, independent to dependent variable, like we might think like there is some relationship. For example, like this one, like grade and happiness. Increase of grade might increase happiness, maybe, right? But how about we think grade actually increase self-esteem, and increase of self-esteem is actually one predicting happiness. Like which one is more sounds right? Like, you know, which one is more sounds better? You know, how are you going to test it? Like between these two statements, grade goes to happiness or grade self-esteem happiness. You know, these two we have these two thinking, two sentences. Then, yeah, what do you think? No, we have time, so I think like, what do you think? I ask. I lost everybody. Alright, so we're going to use, Baron and Kenneth steps, resetable regression, and use Sobo test bootstrapping Monte Carlo simulation for the significant test. Yeah. It's easy, it's not that complicated. So I think we can get it today. Everyone can get it. Independent, as I just stated, we have three variable: independent, mediator variable, and then dependent variable for the mediation analysis. So we have to remember that there is A, B, C prime, and C paths. That's called paths. So we call independent to mediator variable is A path, mediator variable to dependent variable B path. Independent dependent variable is C path, and we call it total effect. And what we see, how we test these two relationship is by comparing C prime direct effect with the mediation and the total effect. So we are going to use regression, and we will do three regression and see how total effect changes when the mediator variable included in their model. And then we compare with the stat test is apply on how direct effect and total effect difference. That's how it goes. So check this out. We have 3 steps. Baron Kenneth's 3 steps. It's like a 1986 stuff. So it's 40 years ago. So for the total effect, first we need a relationship x to y. We need this relationship. X like a grade goes to happiness. So they claim it's supposed to be significant. But it turns out later in 2002, we don't need total effect to be significant for the mediation to be significant. So even if it's significant, it's better. But if not significant, with the solid background theories, actually we can state it's not conclusion for the. It's not conclusive to say there's no ground for mediation. We can still have mediation. So that's what I'm saying. So step 1, this is a regression model. Y regression on X, whether X can predict Y. Simple linear regression here. The C path. It's nothing is fine. And the step 2, we now include the mediator model, mediator variable, and we now predict X, independent variable, to the mediator. How do you think? It's supposed to be significant. It should be. If we want to claim mediator is mediator, If not significant, you get this cat face. If not, you cannot say this mediator is mediator. Mediator is just some random third variable, In the third step, now we include the
cat face represents.
What the cat? That facial expression. How did
what cat face represents?
Yeah.
I don't understand.
Cat face. It's like sad cat face.
Yeah.
Yeah, it's both.
I don't understand what cat face represents.
Oh, okay. If not, you have a hard time. If not, you have a hard time because your mediation analysis is go to trash. Okay. It's hard. So now third step include in the linear regression model we include the x and m, which is the independent variable and then mediation variable, and then now we compare this coefficient of x and m. Oh no. This C prime to the total effect, direct effect, total effect. That's what's going on. And the flow chart saying, so that's pretty much like that. Regress y on x. If not, it's still you can still go on. If regress on m on x, if not, you got no ground for mediation. So just give up. And if fine, regress y on x and m. Y on x, does x predict y? If C prime is significant, then means you have no mediation effect because total effect was significant and C prime with the mediation still significant. It doesn't make sense. Mediation like have no effect between this model. But what you're supposed to see is C prime is not significant when mediator effect variable is included. Okay? So we see direct effect becomes not significant, but total effect is significant. That's how we compare it. And how are you going to comparing? You're going to use this Sobel test or bootstrapping, Monte Carlo simulation. So back to MATLAB. Okay. So right now,
Yes, explain what's the bad test and bootstrapping for in this case. What's the bad test? Bad test is what in this.
yeah, Sobel test.
Yeah, yeah.
It's for statistics.
I mean, what's the aim of the test?
To show that like the mediation so we have this path coefficient from the regression models.
Yes.
And then now we need to compare this path coefficient is significant difference or not.
Yes.
So we use this Sobel test.
Okay, so the bad test is basically for the mediation result examination.
It's for summary statistical inference between differences of path coefficient.
And how do you read the result when the result is significant?
I think I can just show right now actually. Like you can just run it, okay? Because for the data this is like a just short XM and XMY. It's just 32 the samples, and actually I just run this code, this demo code. You directly get this result. You can just test. Like so what we just tested was yeah. So statistics for these three regressions, of course, comparing these three regression models and their coefficient.
So it means that in the path analysis, bad test result is p equal to.
Yeah. So the result we get p.
It means that when the p-value is smaller than 0.05, then it's significant.
Yes.
Examination effect.
But we still need to comparing. We still need to compare between whether the p is significant between direct or indirect and in total effect. We need to compare these p values across the variables and paths. So it's easy, and this code actually just show all the result for whatever you need, right? Regression, step 1 to 3, and path analysis, and summary, no conclusion. So that's what happens. So I have this I already have found this data for use this simulation. So if you want the full mediation, you can still find it. I will just show it. I'll just demo right now. How about no mediation? So as I just said, for initiation, we have regress y on x, m on x, y on both x and m. This three regression, we get it, and we get like this direct effect, indirect effect, and total effect for the further test. And in this code, we have three: Sobel test, Monte Carlo test, conjunctive test. But I'm going to talk about. I mean, it's strongly recommended to use bootstrapping or Monte Carlo test. So, yeah, let's just try. And then summary. Get out. Like we got like all the p-value and three different test results. For the visualization, we run the remaining stuff, and finally we get this. So if you take a look, x to y total effect was significant p below 0.05, which is 0.03, which is not really significant, but anyway, it's still significant. And in the mediation regression, we found that x to m is not significant, which doesn't tell us any of the mediator variables rule in their regressions. So although their total effect becomes insignificant, but it's telling us actually mediator variable has no relationship with the x, but still they can predict the y, that's why it's still, but mediation role is not significant, so we cannot tell there's mediation. And another example, how about full mediation? See, x to y total effect 0.01, which is significant. And now in the mediation regression, total effect becomes very insignificant, and x to m becomes significant, m to y significant, very significant. So we can say that this is full mediation effect, which is mediator actually took up all the variance between a total effect. So mediation happens. And what about no conclusion? X to y total effect was not significant, but x to m to y was significant. This happens according to other researches. So there's although there is no conclusion, we cannot really say there is a ground for mediation, but still there was mediatory effect, even the total effect was not significant. That happens. So okay, that was an example for the mediation analysis. So how about in the fMRI then? So fMRI, this study is 2017 in January. So Johan Weber, he is the author of NeuroElf. Johan Weber in Columbia University. Yeah. I talked to him one time. Okay. Anyway. Anyway, we see that in this study, like they have this behavioral response upon this choice, and in the mediation analysis, so brain activation with the behavior response, total effect was significant. It stopped. Okay. But with the prefrontal cortex activation, amygdala to prefrontal cortex as the mediator to the behavioral response becomes significant, and without direct path significant. So which means it is full mediation through the prefrontal cortex. So stating there is like this two-way relationship has been found for this affective response. So amygdala and prefrontal cortex work together maybe for this for inducing this some stuff, Yeah, that's how we use in the fMRI. So now I will use NeuroElf to show how to do it in our data in our couple shopping. Okay, clear. So we have this folder, couple shopping mediation, and I already have loaded all the required resources, including the VOI and the GLM. It's not that big. It turns out it's not really big. So yeah. So let me open URF GUI.
So basically, you just change from behavioral regression to PPI.
Yeah.
A series of PPI.
So it can be like many different ways. It can be like the independent variable, mediator variable, dependent variable can be anything. Like it can be like behavior to the two brainwave, or it can be like 3 ROIs, or 2 ROI with the behavior response. But I guess like a 2 ROI with the behavior response is more classic or yeah. Okay, so we have neural health. Thanks to your member, okay? So, and I will open the GLM. GLM. And analysis. Single level RFX mediation. So you get a warning saying like X and Y cannot be the same term. Okay. So I'm pretty sure there's important the important part. There's a bug, okay? There's a bug. I mean, you cannot change this one. You cannot change this mediator, you know. So please remind that change contrast first and back to covariate. Now you can choose this, you can change this M. See? This is important because initially you cannot choose it. There's some bugs, okay? It's not like perfect program, so you cannot change it, okay? So please contrast and covariate and then you can change it. Yeah. Yeah, that's it. I already loaded yeah, I think I forgot to show this one, but so in the GLM model, I already loaded this available covariate that computed. I already have it. So you don't need to do this part, but yeah, if you want to use in your data, you might need to do it. But anyway, yeah, repeat it. Yeah. So in this case, superior ST, I don't know, it's TPJ or something. I use this 3, and I will use Monte Carlo simulation here, and I'll compute. The result is shown in the MATLAB, which is T-stat suggests C-pass was significant, PO2. AB and AB pass significant, and most important, C prime pass become insignificant. Direct effect known, but mediator effect significant. So it is a full mediation between these three brain regions. So it's a like actually big find, okay? It was pretty good things, you know. So you can test different ways, definitely, across different brain areas, maybe like 1, 2, 3, 1, 2, 3, 2, 1, 3, 3, 1, 2, 2, 3, 2, 1, maybe. You get the different way, you get different result. So in this case, what? Yeah, it's still quite significant, but A is like a less significant, but yeah, whatever. Yeah, that's it. Mediation.
I guess you need to go slowly again about in parallel to the behavior. So what is Y and what is X and M as the RI in the URL. So that is good.
Okay. So actually, I have these 3 RI regions of which are derived from previous result. I think I should open manuscript. Let's see. Oops. I don't have. Actually, it has been updated, but anyway. So in this study, we had identified these 3 brain regions very adjacent. It's around this TPJ, IPS stuff, IPL. These 3 brain regions are identified by different context. And we wanted to see like how these three brain regions actually associated. That's why I used the mediation and these three close brain regions. Okay. So this is the three brain regions that I used in here, which is one of them is IPL and one of them is TPJ and one of them is anterior IPL. Okay. Yeah. In the contrast of conflict minus consensus. So we are using actually the GLM result.
But usually we put in this cell the behavior index of each individual. What do you actually put here? Because it says BOI or something. What are those variables?
Behavior.
I mean, what are those variables in the cell?
This one.
Yeah.
This is the VOI time series. This is identified from the GLM contrast. That's the covariate. But the thing is, we are not using this for GLM right now. We are using this for the random effect, the
mediation.
Mediation. So this is not used in the GLM, but it identified from the GLM. So that's why it shows up here.
Okay.
Yeah. So these three brain regions.
So how do they end up in there? I mean,
I saved it, like and loaded it here.
And how do you save it?
How do I save it?
Yeah.
Actually, I forgot. I have to do it. Let's see. Like for example, like conflict minus consensus. Let's compute it. And we got the.
So this is a regular contrast. What you have done is regular contrast.
Conflict minus consensus.
Okay. Conflict minus consensus.
Oh wait. Why is it blue though? Oh, maybe I should. It's different. Consensus. Let's see. Two. Am I doing right? Let's show up some TPJ. Okay, for example, like if you want this one, too much, too less. Let me just show it. I think it's around these areas. It may be like slightly different, but anyway. Beside that, if you have this one, we can save it as a VOI. We can save it as VOI, and then we just load it here. Okay, maybe not. Okay, I literally forgot. Oh, okay, I got it.
Oh, I never tried this. So this can also load the VOI into the.
Yeah. So we first load here in the main window, and then in contrast manager, like we click this second one.
So what you didn't explain is that because I think in morning's class, usually they load here with the behavior index across each individual.
Yeah.
So that represents how each individual is doing. But here you load the VOI.
Yeah, I define it and then we load it.
Okay, so
and if we load here in this GLM part, and then there is automatically we can find here, like here.
Okay.
Yeah.
If you load 3, then 3 will appear here. Okay.
Yeah.
So So you need to do you need to load those BOI first in the contrast icons, and then try to do the mediation analysis later.
Yeah.
Okay, so that's the first part. And second part, here after you load those BOIs. How do you input each? How do you use each as a Y or X or M?
Oh, okay. I will do it. Let me check. Crap. Should I do it again? Let me clean it. Okay. Crap. It's gone. Oh. I will
download again.
Yeah, I think I better download it again.
Yeah.
This is.
So you change it. Yeah.
Let me see.
Automatically change the.
I will find whether I can load it.
Because you update to the GLM file.
Yeah, it's just saved. But let me just open the file system just to see.
它就是会就是 information 啊，你要注意看，它就跟你讲它做什么事情，information 按键是做什么，就像那 Windows 不是会有跳出来那个反白的情况上面写。
Okay, I got it back.
So you have 3 VUI there, and then you do the
this part.
Okay.
So it automatically detects the ROI covariate.
So which part you want to be Y?
Oh, okay. That's the part. Like, so here is X, which is independent. Y here, dependent, and mediator is here, in left bottom. And C is covariate, which is we don't need. So, it's like a covariate in our mediation regression model. So it's something else. So we have X, Y, M.
So usually you just need one in X, and one in Y, and one in M.
Yeah.
And you don't need C, right?
Yeah. We don't need C. You don't need to click anything.
Okay, but it says here M is consensus versus consensus group minus conflict minus consensus is not the BOI. So how do you interpret?
So there is like a way we can in the URL we can actually use the whole brain map as a variable, so we can detect whole brain of like various brain regions have a mediation role in the between X and Y. So that's the one way of the doing mediation, whole brain mediation, right? But we use covariate, use the ROI based one. So actually, this covariate ROI region can be whole brain contrast map from GLM. That can be done as well, if you want.
So what do you use as Y? The inferior parallel lobe, and X is the superior temporal teres, and M is the TBJ, supermarginal.
Yeah. Okay. I will go get some water. yeah, that's it, I guess.
Okay. So, so there's no PPI here, right? You're just doing contrast.
PPI, no.
So you're just doing contrast between. You're just showing the contrast of three ROIs, showing some mediation effect.
Yeah, this ROI, yeah. Yeah, that's true, I guess. Yeah.
So there's no PPI
No.
functional connectivity involved
Oh,
in
no,
the
no, no,
in the
no.
analysis
Yeah.
here.
Any question?
不一定吧，它只要露一下哦，UI 程序应该就可以做了。是的，你自己可以试试。
Oh, yeah, I think I did that. Yeah, this like it's like how do you like report the result of mediation? Like you have to state like the path coefficient and then confidence interval and p-value, and yeah, that's how you need to how you write down the result.
Usually C represents what?
C is just C, the total effect.
You mean from X to Y?
Mm-hmm. I mean, in this study, I just copied.
Let's see, AB.
Can you see?
One.